civil engineering majors, mechanical engineering majors, I don't think you have to take modern physics, but the rest of you guys will have to. Okay, and modern physics is a lot of fun. So it's fun to see the evolution of physics through the hydrogen atom. All right, everything is related to the hydrogen atom. So what do we have regarding the hydrogen atom? So let's take a look at the magnetic dipole moment of the hydrogen atom and why things become magnetized. All right, so how much time do I have? Okay, 10 minutes is good. All right, so the magnetic dipole moment. Of hydrogen atom. This normally would be a test question. This would be an extra credit test question. Traditionally, at least traditionally by me, because I normally would teach modern physics right after this. Just want to make sure that everyone is prepped for it. All right, so here's what you got. You got the electron moving about the nucleus. All right, so which means that this would create a current, and if there's current, which means that there's going to be magnetic field. All right, so which means that the atom would become magnetized. It would become a dipole. All right, so now it acts like a dipole, which means that its magnetization factor, or how much it acts like a dipole, can be represented by mu. All right, so the question is, what is the mathematical expression for mu? All right, so straightforward. Number of turns, area, times the current. All right, so number of turns in this case, just remember this for the future, is the number of electrons that it's got. Number of loops is going to be the number of turns, just the number of electrons. In this case, we have only one electron. That's the key thing about the hydrogen atom. It's the most simplistic model that we can have. And because there's only one single E electron that we got. That's it. Area is going to be pi r squared, so we're good with that. Which means that I might as well just say r is the radius. So let's denote that. And now we need to come up with an expression for current. So what is current? Current is going to be the net charge per time. We only have one single charge per time. All right. Now we have to come up with an expression for t. We need to come up with an expression for t. All right. This is where it kind of gets confusing for you guys because this is your first or second attempt at physics. You guys have done some heated physics in high school, most of you guys. And this is where it gets confusing because now you need to know what t is. We've got nice little expressions. Guys, what is t? The current is the net charge per second, right? What do you think t is going to be in this case? I would say its t is going to be the time for it to actually complete one single loop. Got it? So you kind of have to make that connection. So the current in this case is going to be how fast the charge is just going to go around the single loop that it's going to come up with. All right, so this is the same as tau that we were discussing before. So we will just express it in terms of period. All right, imagine that this is the period of this. All right, so do we know how to find the period of this? Yeah, we do know how to find the period. So what I'm going to do is we'll do it exactly the same way we did it before. So here's what we got. We got the charge moving at a given speed. Charge is going to move in this direction at a given speed. All right, it's got a radius. And so there's going to be a force acting on it. So this is the centripetal force. There's positive charge, got a negative charge. So the centripetal force is the same as the electrostatic force. All right, so there's electrostatic force acting on it. And it's got speed. All right, so what I'm going to do is I'm going to get this from the speed itself. All right, the period, you can get the period from speed. So you got 2 pi r divided by the speed. All right, and this is the same as 1 over t. All right, so I already captured this expression here. I can actually plug this back in here. This will give me my current. All right, so what I need at this point is the speed. I can get the speed out of here because this is your circular motion. All right, so what do we know? This is our circular motion. Electrostatic force is the same as the centripetal force. All right, the electrostatic centripetal force is going to be mv squared divided by r. electrostatic force is going to be K. All right, so let's have a positive charge here. So this is going to be Q1, this is going to be Q2. We're interested in the absolute values of those. And I'm just going to simplify this. Q1 and Q2, these are unit charges. All right, so it's going to give you mv squared divided by r, ke squared divided by r squared. All right, cool. All right, all right, I'm looking for, checking to see if we will have any potential problems. I don't see any potential problems. All right, all right, so let's take care of our cancellations. And that's it. Solve for B. All right, so we will have K E squared. What else? We have MR. All right, I came up with an expression for speed. Just for the hell of it, I'm gonna just bring this out. All right, it's a cleaner expression. All right, so now what do we do? All right, so boom, plug this in there, and then this expression. So this expression is going to go in there, and then that expression is going to go in there. All right, so back substitution after back substitution. All right, so the first thing that I'm going to clean up is take this in there, and then come up with this expression. All right, so just 1 over t. It's going to look like 2 pi r divided by v. All right, so keep this out there. I see that we could do more cancellations, but I'm going to wait on it. And then the next thing I'm going to do is I'm going to take this expression. All right, so we got to grab this expression and then place it right there. So, which means that this is what we were doing in order to get current out of it. Obviously, we have a cancellation there. All right, so so these two end up canceling, so we are good. Got our current. All right, so I'm just inverting. I end up inverting this expression. All right, so where are we now? All right, so we are right here. I think we're done with that one. All right, so this expression is going to go here, and then the current is going to go up there. So, all right, so we have to put the area here, the current here, and then I think we're done. Area is going to be pi r squared. The current is going to be that expression. Ooh, and then let's just clean it up. All right, so you got pi and you got pi, so it's going to be pi squared. You got r squared, you have r. So it's going to be r to the cube. We got an r here. Okay, so we got 2 pi squared r to the cube. What else? All right, that's it. All right, so you can keep playing this game more like I can. All right, this goes up to square both sides and take the square root of it. I wonder if there's a mistake that I made somewhere. I don't like the expression. This is kind of weird. Anyway, so we came up with an expression for mu.